Okay, so let's resume our discussion after that mild technical issue. So once we have our two ion charges, we want the ratio of ions to be the simplest, smallest whole number ratio. So if we cross our charges, we would predict a formula of barium 2, carbonate 2. However, is there a simpler ratio than 2 to 2? So what can we simplify this 2 to 2 ratio? What can we simplify this 2 to 2 ratio to? 1 to 1, exactly. So a more accurate formula would be barium carbonate, which is a 1 to 1 ratio. So you always want the simplest ratio of ions as long as it's the smallest and simplest whole number ratio. Now, one thing you want to do just as a check is you want to verify that the total charge of the ions match the total charge of the ionic compound. So let's look at sodium oxide, Na2O. So in this case, we'd have sodium plus, and how many sodium cations do we have? How many sodium ions do we have based on the formula? How many sodium ions do we have? 2. Yep. So let's put the charge of +1. We have 2 of them. And now let's add the charge of our anion. So what's the charge of oxygen? What charge do we find for oxygen? What's the charge for our oxide anion?
Two minus.
Yep, exactly right. And how many oxide anions do we have? How many oxygen atoms do we have?
1.
1, yep. So we verified 2 minus 2 is in fact 0, and all is right with the world. So we can also do the same process for barium carbonate, where we have +2 times 1 plus -2 times 1, and that also checks out to be 0. So our total charge of all of our ions matches the predicted total charge for our compound. Does this process make sense to everyone so far? So first you figure out the charge of each of your ions, then you cross the charge of each ion into the subscript of the opposite ion. And finally, you just check your work by verifying that the total charge of your ions match the total charge of your ionic compound. Does this make sense to everyone so far?
Yes.
Perfect. So let's do a guided example now where we work on the following 2 problems. So we have to write the chemical formula of an ionic compound containing iron 3+ and S2- ions. So I gave you the charges in this case. This is just to check your fundamental mechanics with this process. So we take each of our charges and we cross them into the subscript of your opposite ion. So that gives us Fe2S3. We can check our work really quickly by just verifying that the total charge is in fact 0. And we've verified that to be true. So barium oxide next in this next example is composed of barium ions and oxygen ions. So we have to write the chemical formula of barium oxide. So first and foremost, barium, which is a 2A element, will adopt a preferred charge of +2. Oxygen, which is a 6A element, adopts a preferred charge of -2. So for barium, 2+, oxygen, 2-, we cross our charges, and that in turn gives us barium 2O2, which we can simplify to barium oxide. Does this process make sense to everyone? Any questions on these examples? If not, let's take about 3 minutes and let's try to propose a formula for the following two problems. This, just as a side note, make sure to take notes of your proposed solution in your note set. We'll discuss the solution in about 3 minutes, and then you can retake or reattempt this problem using the Canvas quiz feature either tonight or tomorrow. And if you have any questions about this process, don't be shy to message me in the chat or unmute to ask your question.
Should we also have these ones done by tomorrow when all the quizzes are due?
The quizzes are all due on Sunday.
Okay.
Yeah.
So we should have the ones from chapter 3 that we've been doing today done as well?
Yes.
Okay.
Yeah. Mm-hmm. Yes. So all of the assignments are going to be due Sunday in this case, just to give everyone a little bit more time and just so that way more of the weekend can be used to catch up. Mm-hmm. I'm already seeing some reasonable responses in the chat. Let's take about 2 more minutes to discuss and work through these problems. And don't be shy to message me with any questions or any proposed solutions. We're seeing some reasonable responses in the chat. Let's try to get a few more responses, and then we'll discuss in about 1 minute. Okay, I'm seeing a large number of reasonable responses. So let's now discuss this question. So first and foremost, aluminum 3+ is given, nitrogen 3+ is given. We cross our charges, we get Al3N3, which we can simplify to a 1-to-1 ratio of aluminum nitride. For silver phosphide, it's composed of silver ions and phosphide ions. Silver is a fixed charge transition metal that adopts a charge of +1. For phosphorus, which is a 5A element, phosphorus prefers to adopt a charge of 3-, because 5 minus 8 is -3. So now that we have silver plus and phosphorus 3-, we cross our charges. And that in turn gives us Ag3 phosphorus or phosphide. That gives us the following formula for silver phosphide. Any questions on these examples? Any questions on these examples? If not, let's continue on with this by working on a few more examples. So this is another guided example. This time we're dealing with some polyatomic ions. So lithium carbonate is composed of lithium ions and carbonate ions, and we have to write the formula for lithium carbonate. So lithium is Li, it's a 1A element. So what charge will lithium prefer to adopt? What charge will lithium prefer to adopt? What's the charge of lithium in ionic compounds? Yep, +1. Carbonate. Would someone like to propose a formula for carbonate, ideally with a charge? Yep, CO3 2 minus, exactly right. So carbonate is CO3 2 minus. We cross our charges, and that in turn gives us Li2CO3, or lithium carbonate. Okay, let's look at this next example. Zinc phosphate is composed of zinc ions and phosphate ions. So zinc is a fixed charge transition metal that prefers to adopt a 2+ charge. Would someone like to volunteer and provide the formula for phosphate? What is the formula for phosphate? Yep, PO4 3 minus. So we have zinc 2 plus for zinc, and for phosphate it's PO4 3 minus. We cross our charges, and that gives us zinc 3. And remember, you put the entire polyatomic ion in parentheses and then apply the subscript. So we have PO4 subscript 2. Does this make sense to everyone so far? Don't forget to put your polyatomic ion in parentheses. Otherwise, your subscript may not apply to all of the atoms that you need it to. Any questions on this example? Any questions on this example? Okay, so let's now take about 3 minutes and let's work through the following 2 examples. And don't be shy to message me your proposed formulas using the chat feature. And don't be shy to ask questions via the chat or verbally. So let's take about 3 minutes to work through this, and then we'll come together as a group to discuss. And I'm already seeing some reasonable responses in the chat. Let's try to get a few more responses before we discuss, and we'll discuss in about another minute and a half. And don't be shy to message me either privately or publicly with your proposed response, just so that way I can provide feedback. Okay, so let's now discuss these examples. So ammonium chloride is composed of ammonium ions and chloride ions. What is the formula of ammonium? When we say ammonium, what does that represent? Ammonium represents what? NH4 plus, exactly right. So we have NH4 plus, and then chloride. So chlorine is a 7A element. 7 minus 8 gives us -1. So we have NH4 plus and Cl minus. We cross our charges, and that gives us NH4Cl for ammonium chloride. Okay, let's look at scandium bromide. Scandium, as we've seen in previous examples, it's a 3B element, and it's one of the exceptions for our transition metals, and it prefers to adopt a +3 charge. Bromine is also a 7A element, and it prefers to adopt a -1 charge. So we cross our charges, and that in turn gives us scandium with 3 bromines as part of the formula for scandium bromide. Does this make sense to everyone so far? Does this make sense to everyone so far? Any questions so far? If not, we'll continue on with nomenclature. So, one idea that I want to introduce is that these previous examples were designed to cover most cation and anion charge combinations. Notice how the formula and the logic that we use to calculate the number of each cation and anion only cares about the charge. It doesn't actually care about the identity of the cation and anion. As a result, you can replace any ion in an ionic compound with another ion with the same charge, and you get a new valid formula. So just to illustrate this point, iron sulfide is Fe2S3. That's composed of iron 3 plus and S2 minus. We can just as easily look at a somewhat tangentially unrelated compound. So aluminum oxide, we have aluminum 3 plus, same cation charge, O2 minus for oxygen, because 6 minus 8 is -2. And because our charges are the same, when we cross our charges, our overall formula will be very similar if your charges are identical. Now, the real important thing to note here, and to really tie this all together, we can just as easily replace this aluminum with any cation with a +3 charge, and we'd still get a perfectly valid formula. We can also replace oxide with any anion with a 2- charge, and we'd also get a valid formula. So this is often how people can write the formulas of ionic compounds very quickly. They're using analogy. They've already gone through this process of writing the chemical formula for one type of ionic compound, and because the charges are identical, when you show them another ionic compound with the same charges, it's a pretty fast process. So for example, if we're dealing with a compound formed from iron 3 plus and sulfate, so we have iron 3 plus and SO4 2 minus. Our charges are the same, so our overall formula structure should be the same. Does everyone notice how the formulas look very similar for iron 3 sulfate and aluminum oxide? Does everyone notice how the formulas structurally look very similar for these two compounds? Well, do you notice how for our cation, we have 2 aluminums up here and we have 2 irons down here? And for our anion, we have 3 oxygens up here and we have 3 sulfates down here? Do you notice how the number of cations and anions in each of these two formulas are identical because our charges are identical. Does that make a little bit more sense? So essentially, the method that we use only cares about the charges. So if you have a cation and you wanted to write the formula of, let's say, a new compound, you can just as easily replace your cation with any cation with the same charge, and you'd get a valid formula. So this is helpful because when you encounter a quote unquote new compound, if you can identify the charge, you can quickly write a formula via analogy. So let's showcase some of this utility. Why do we care about this? Well, let's look at these next few examples and let's see where we can begin to try and save some time. So iron 2 cyanide consists of iron 2 ions and cyanide ions. Okay, so based on the name for iron 2 cyanide and based on our rules, what does this Roman numeral tell us? What is the charge of iron based on this Roman numeral? What is the charge of iron? 2+. Okay. Cyanide. Would someone like to provide the formula for cyanide? Cn-, exactly right. So now we cross our charges, and that in turn gives us FeCN parentheses 2. Again, make sure that you place the polyatomic ion in parentheses. If you wrote this, this would not be correct. Does that make sense to everyone? Any questions on this example? Okay, let's look at another example. Tin 4 sulfate consists of tin 4 ions and sulfate ions. So what's the charge of tin in this case? What is the charge of tin in this case? Yep, +4. Sulfate. Would someone like to provide me the formula and charge for sulfate? Someone like to provide me the formula and charge for sulfate? SO4 2-, exactly right. So now we cross our charges, and that in turn gives us SN2 SO4 4. Can we simplify this ratio? We currently have a 2:4 ratio. Can we simplify it? Can we simplify it? Yes. So let's simplify it to a 1:2 ratio. And we get the following formula for tin 4 sulfate. This 4 is the charge, not the number of ions or anything like that. It's just representing the charge. Okay, let's take a moment to work on the following two examples and try to see, look at the earlier problems and try to see if you can save some time by drawing formulas via analogy, if you prefer. Otherwise, let's take about 3 minutes to work through these examples, and don't be shy to message me your proposed solutions using the chat function or unmuting and asking a question. And we'll discuss in about 3 minutes. So I'm seeing some reasonable responses in the chat, but let's try to get a few more responses and we'll discuss in about a minute and a half.
Sorry, I didn't quite catch.
Sorry about that. Let's try to get a few more responses in the chat. We just want a reasonable pool of students. So that way I can provide some feedback and see how the class is doing on those problems. And just make sure you're double checking the charges for each of these component ions using the charge rules. And we'll discuss in about another 30 seconds. Let's try to get a few more responses during that time. So that way we can have a robust class discussion. Okay, so I see a lot of reasonable responses so far. So let's discuss this next problem. So lead 4 acetate. So lead 4, what is the charge of lead in this case? What is the charge of lead in this case? Four plus, so we have lead 4 plus. Acetate, would someone like to provide the formula for acetate? C2H3O2, sure. And what is the charge? What is the charge? -1. Yep. Another way of writing acetate would be CH3CO2 minus. This is preferred if you're potentially taking organic because provides more structurally rich information on how the atoms are connected, but both methods of portraying acetate are fine. I will prefer to use this method though. Anyway, so we'll take our charges and cross them, and that in turn gives us lead with 4 acetate anions. So this is the formula for lead 4 acetate. Let's move to cadmium nitrate. It consists of cadmium ions and nitrate ions. So cadmium is a transition metal, but what's special about cadmium? Can we assign a charge to cadmium? Two plus, exactly right. Okay. Cadmium is known as a fixed charge transition metal. Nitrate is NO. What is the formula and charge of nitrate? What is the formula and charge of nitrate? Yep, so it's NO3 minus. To answer the question in the chat, aluminum is not a transition metal. It's a main group metal. Cadmium is considered a transition metal, and because it's a fixed charge transition metal, we have defined rules for predicting its charge. Perfect. So now that we have each of our charges, we're going to cross our charges. Oops. Going to cross our charges. And that in turn gives us cadmium with 2 nitrate ions. So this is cadmium nitrate. Any questions on this example? Any questions on this example?
Yeah, I have a question on the first one though. I got confused as why does it look like that? Like what happened to the C2? Why is it now CH3CO2?
These are two ways of writing acetate. If you prefer the other method, we can write it as PbC2H3O2. Both are common, and the further along you go in chemistry courses, the more you'd prefer probably this top method, because there's most of the time chemists are biased towards writing formulas in a way that gives us structural information. So this first way of writing acetate is pretty common. If you look at like Wikipedia articles and other sources where they're discussing chemistry, this first method is more information rich in my opinion, but both are perfectly fine.
Would you be able to explain how you got it like that, or what's the logic behind it?
So acetate, like structurally, if we look at what acetate looks like in terms of how the atoms are connected, essentially the way that we've written out acetate showcases and indicates the atoms going left to right in our structure, respecting its connectivity. So all we did is just moved one of the carbon atoms in this formula after the hydrogen, just to represent the fact we have a CH3 and then this CO2 group.
Okay.
So that's the reason why we like to write the formula that way. However you write the formula, even on Canvas, it will accept both of them and you'll still receive credit. It's just a matter of personal preference.
Got it. Okay, thank you.
Any other questions on this example? If not, let's continue on and let's talk about how to predict the ion charge from the chemical formula. Now, this is really important for transition metals because transition metals can adopt a variable charge. So we need to figure out the charge of our metal cation. So we know that the total charge of an ionic compound is the total charge of each ion, right? So this equation we've used time and time again. Now, the total charge of a neutral ionic compound is going to be 0, right? So we'll set this entire total charge equal to 0. Now, oftentimes, the charge of the anion is pretty easy to figure out. We can figure out the charge of our anion from periodic trends or using the common charges for polyatomic ions. So both of those are readily available. For the periodic trends, of course, you're going to use the periodic table. For the polyatomic ions, you're going to have to recall those from memory. So if you know the charge of one ion, we can actually solve this equation for the charge of our cation, and that gives us the following equation to calculate the cation charge. One thing that we want to note is whenever you see an equation, you need to get a sense of what the assumptions are, and this assumes for a neutral molecule. So for a neutral, let me rephrase that, for a neutral compound, well, yeah, neutral compound would be preferred. So this applies for a neutral compound with 0 total charge. So let's show how this formula works in action. I mean, the utility of a formula is best shown by how it can solve problems. So in this case, we're asked to figure out what is the charge of tin in tin. You know, here's the thing, when I try to say its name, I'm going to end up giving away the charge on accident. It's pretty common with these because I'm so used to calling these compounds by their actual name. So what's the charge of tin in this compound here? So the charge of tin is equal to -1. And we know that chlorine prefers to adopt a -1 charge. So we're going to take -1 times the charge of our anion, which is chlorine, which is -1, times the number of anion, which is 4, over the number of cation. Oops, one moment. And how many cations do we have? How many tin atoms do we have? How many tin atoms do we have? Just one. So that in turn gives us a charge for tin of +4. So this would be tin 4 chloride. Does this process make sense to everyone? Any questions so far on this process? If not, let's continue on now. And let's do a few guided examples. So in this case, we're asked to figure out the charge of vanadium in vanadium hypochlorite, in vanadium chloride. So ClO2 represents chlorite. Would someone like to tell me what is the charge of chloride? What is the charge of chloride? -1. Okay. So then we now have enough information to use our equation. So the charge of vanadium is equal to -1 times the charge of our anion, which is -1, times the number of our anion, which is 5, over the number of cation. And that in turn gives us a charge for vanadium of +5. Let's now apply this equation. Let's try to figure out the charge of an anion X in Al2X3. So we know that aluminum, being a 3A element, prefers to adopt what charge? What is the preferred charge of aluminum? What is the preferred charge of aluminum? Three plus, yep. Okay, so then we now have enough information to solve for the charge of X. So the charge of X is equal to -1 times the charge of our cation, which in this case is +3, times the number of cation, in this case, which is 2, over the number of anion, which is 3. And that in turn gives us a charge of -2. The way that we got this equation is by rearranging our given equation to solve for the charge of our anion. So we get the charge of our anion is equal to -1 times the charge of our cation times the number of our cation over the number of our anion. That in turn gives us a predicted charge of -2 for our unknown anion X. Does that make sense to everyone so far?
No, I'm sorry, it doesn't. So like for the first one,
Yep.
how do you get a charge of -1? Is it because, let's see, 5B ends up being a -1 charge?
So looking at chlorite, what is the charge of chlorite?
Chloride.
Right
Oh,
here.
-1.
Yep, so that goes right here. The -1 is just part of the equation. The 5 comes from the fact we have 5 chlorite ions, and the 1 comes from the fact we have 1 vanadium. Does that make sense?
Okay. Wait, so the so V, what is that? Is that -1?
So vanadium, we're trying to figure out the charge. And in order to solve for the charge using this equation, we take -1 times the charge of our anion, which is -1, times the number of our anion, which is 5, over the number of vanadium cations, which is 1.
Okay.
Does that make sense?
Yeah, it does. Okay, thank you.
Perfect. And you're not required to use this equation. In fact, there's going to be a slightly simpler method that I'll show you in a moment. But I want everyone to be familiar with this equation because it does have important cases where it's the only thing that will be effective for solving some problems. So let's take a moment, and as our last activity for this session, let's try to figure out the charge of an atom in the following two compounds. So let's take about 2 to 3 minutes to work through this problem, and don't be shy to propose your solution via the chat, either publicly or privately. We're already seeing some reasonable responses in the chat, but let's get a few more responses before we discuss. And let's spend about another minute and a half. And let's try to get a few more responses in the chat, just so that way I can get a sense of how everyone's doing so far. I'm seeing a lot of reasonable responses, but let's try to get a few more before we discuss. Okay, so let's now discuss this problem. So first and foremost, let's look at NO2, which is known as nitrite. What is the charge of nitrite? What is the charge of nitrite? From our table of polyatomic ions, what is our charge for nitrite? -1, yep. So then the charge of titanium is equal to -1 times the charge of nitrite times the number of nitrite ions over the number of titanium ions, which gives us the charge of titanium of +4. In the next example, we're looking at the charge of the anion X in magnesium X2. So then we know that magnesium, being a 2A element, adopts a charge of 2+. So then the charge of magnesium is equal to the charge of X is equal to -1 times the charge of magnesium, which is +2, times the number of magnesium atoms over the number of X atoms. And that in turn gives us a charge of X equal to -1. Does this example make sense to everyone? Does anyone have any questions on this example before we close out today's lecture session?
I'm just getting confused as to which one's a cation and then which one's a charge of the anion and then the number of anions.
Okay. So in the first equation, this number here is the charge of our anion. This number here is the number of our anion. and then we're dividing by the number of the cation. If we're dealing with solving for the charge of an anion in this top equation, this number is the charge of our cation. This number is the number of our cation. And we're dividing by the number of anions that we have. Does that make a little bit more sense?
Yeah, but what I get confused is the actual, like, where it says what is the charge of the anion X and MgX2. That's where I don't know what goes.
So the anion is the species with the negative charge. So the anion is the species with the negative charge. And if you have a metal such as magnesium, the metal is a cation because it has a positive charge. Typically in ionic compound formulas, they have the general form of the cation first, followed by the anion. So then the cation is always the first thing in the formula, the anion is always the last in most cases for ionic compounds. Does that make sense?
Yeah. Okay.
Mm-hmm.
Okay, thank you.
Yep. Any other questions I can address? If not, we'll take a 45-minute break and I'll see everyone back in lab at 12:45. Just because I went 5 minutes over, I wanted to make sure everyone still has the same amount of break time. So at this point, I'll pause, I'll end the recording, and I'll see everyone in laboratory.